Welcome. In this short video, we introduce GIQ, a new benchmark designed to assess the geometric intelligence of modern vision models. The authors of this work are myself, Anekha, along with Matt, Tadeusz, Piotr, Mahsa, Varun, and Guha. Our paper is titled GIQ, Benchmarking 3D Geometric Reasoning of Vision Foundation Models with Simulated and Real Polyhedra. Today's vision models achieve impressive results on many visual tasks, such as generating 3D assets from single images, demonstrated here by OpenLRM on the left and StableFast3D on the right. However, their true understanding of 3D geometry remains unclear. Are these models genuinely reasoning about spatial structure, or just relying on superficial patterns? To explore this question systematically, we use Polyhedra, geometric shapes with clearly defined symmetry, convexity, and complexity. Polyhedra offer a perfect testbed because their precise mathematical properties provide unambiguous ground truths for evaluating models. Our GIQ benchmark includes 224 polyhedra shapes that have been extensively studied by mathematicians for decades or centuries. These polyhedra are grouped into distinct classes: Platonic, Archimedean, Catalan, Johnson solids, Kepler-Poinsot, as well as intricate stellations, compound shapes, and non-convex uniform solids. This diversity allows us to systematically test how shape complexity affects model performance. To rigorously evaluate geometric reasoning, we created two sets of polyhedra images: synthetic renderings generated with precise controlled lighting, and real-world images, photographs of physical paper models taken under challenging and varied indoor and outdoor conditions. This combination allows us to evaluate model performance both in controlled synthetic settings and under complex realistic scenarios. Using the GIQ dataset, we designed 4 core experiments: monocular 3D reconstruction, 3D symmetry detection, mental rotation test, and zero-shot polyhedron classification. Together, these experiments provide a comprehensive evaluation of models' geometric reasoning across diverse spatial reasoning tasks. We evaluated 3 state-of-the-art monocular reconstruction methods: StableFast3D, Shapey, and OpenLRM. Despite extensive training and good generalization performance on standard test sets, these models significantly struggled in our experiments, failing even to accurately reconstruct relatively simple polyhedra, and often completely missing their fundamental 3D symmetry. In our next experiment, we assessed whether foundation models implicitly understand important 3D symmetry elements from single images. Specifically, we tested for the recognition of central point reflection, symmetry through a central inversion point, 4-fold rotational symmetry, symmetry under rotations of 90 degrees, and 5-fold rotational symmetry, symmetry under rotations of 72 degrees. Remarkably, Dino V2 achieved 93% accuracy, detecting 4-fold rotations in challenging real-world images, despite training solely on synthetic data. This highlights symmetry detection as a promising lightweight downstream module, leveraging pre-trained vision encoders. We next evaluated the model's spatial reasoning through a mental rotation test. Models had to determine if 2 images showed the same shape, just rotated differently. Surprisingly, all models struggled, especially when comparing synthetic renderings to real-world photos, often performing near chance levels. Finally, we challenged advanced vision language models like Claude 3.7 Sonnet, Gemini 2.5 Pro, and ChatGPT 04 Mini High and 03 to identify polyhedra by name without prior examples. Although these models excel in general tasks, our experiments revealed significant errors, particularly misidentifying key geometric features such as convexity, symmetry, and compound structures. We further analysed model mistakes, uncovering systematic errors. Models frequently confused similar polyhedral forms, misidentified face geometries, or overlooked fundamental properties like convexity. These patterns show that current models still lack precise geometric reasoning. Our experiments reveal a clear gap. Despite impressive overall capabilities, current foundation vision models lack precise geometric understanding. To help the research community address this, we're releasing the GIQ benchmark publicly, providing structured evaluations to foster advancements in robust 3D-aware AI.